We dream of stars, but the universe may have built a prison. You and I, we've all seen the pictures. The sleek starships gliding through nebulas. The domed cities on alien worlds bathed in double sunsets. It's a beautiful dream, isn't it? Humanity spreading like a dandelion's seeds across the galaxy, colonizing 1,000,000 exoplanets, becoming the cosmic empire we always imagined we'd be. It's the story we tell ourselves when we look up at the night sky, that little twinkle of hope that says, one day we'll be out there. But here's the thing about beautiful dreams. They usually end when you wake up, and the reality we're waking up to is a lot harsher than any science fiction novel ever let on. The universe isn't a friendly place waiting to be explored. It's cold, indifferent, and actively hostile. An environment that seems to have built a cage around our little blue marble. That cage has 4 layers. We're not talking about a single problem we can engineer our way out of, like a better rocket or a faster engine. No, this is a stack of impossibilities. A cumulative wall of barriers made up of biology, physics, economics, and cosmology. Each one by itself might be surmountable, but stacked on top of each other, they form a wall so high, so dense, that the idea of leaving our solar system feels less like a challenge and more like a cruel, cosmic joke. A question that's been buzzing around the minds of physicists and dreamers for decades. Is interstellar travel actually impossible, or are we just not trying hard enough? Think about that for a second. We've sent robots to the edge of our solar system. We've walked on the moon. For over 20 years. We're pretty good at this space thing, right? But when you really crunch the numbers, when you look at the brutal arithmetic of the void, you realize something terrifying. It's not that we're lazy. It's not that we lack the will. It's that the universe itself seems to have rigged the game against us. Every time we think we've found a loophole, the laws of physics slam the door shut. Every time we imagine a generation ship floating through the dark, biology reminds us that human bodies are fragile bags of water needing a very specific set of conditions to survive. And every time we hope for a shortcut, a warp drive, a wormhole, a jump through hyperspace, the silence of the cosmos whispers back, we're not even sure if those things are possible in this universe. So here's the roadmap for the journey we're about to take. It's not going to be a feel-good trip. We're going to explore 4 layers of impossibility, one after the other. And by the end, I promise you, the night sky will look different. Layer 1 is the most personal. It's the human body. We'll look at what space radiation, microgravity, and decades of isolation actually do to a person. Spoiler alert, it's not pretty. We'll talk about the simple truth that our bodies evolved for one place and one place only. A warm, wet, atmosphere-shielded planet with a big magnetic field. And the void? The void wants to turn you into a skeleton in about 90 seconds without a suit. Layer 2 is the big one, the one that stops most conversations cold. The laws of physics themselves. We're talking about the tyranny of the rocket equation, the sheer insane amount of energy required to move a human being to another star, and the speed limit of the universe that makes even the nearest star system feel like it's on the other side of eternity. Layer 3 is a bit more depressing. It's the failure of alternative strategies. Ships. We'll look at generation ships, suspended animation, robot colonization, and every other clever idea scientists have cooked up to cheat the system. And we'll see why, so far, every single one of them falls apart under closer inspection. They all run into the same wall. Entropy, energy, and the simple fact that time is a resource we cannot manufacture. And finally, Layer 4. This is the chilling one. This is the one that keeps astronomers up at night. The silence of the cosmos. If interstellar travel is so hard, why haven't we seen any evidence that someone else figured it out? This is the Fermi paradox. And it's not just a fun dinner party conversation. It's a warning. It's the universe looking back at us and saying, "You think you're special? You think you're the first species to look up and wonder. Where is everybody?" The silence might be the most terrifying piece of evidence of all. It might mean the prison is real, that every intelligent species that ever evolved faced this same wall and died trying to climb it. Or worse, that they didn't even try. That they looked at the math, looked at the biology, and decided it was better to stay home. So, before we dive into that cold, hard truth, I need you to do one thing. If you're ready to confront the brutal reality about our cosmic cage, if you're willing to stare into the void and not blink, hit that subscribe button right now. This is not a happy video. This is not a motivational speech about how we'll conquer the stars with the power of human ingenuity. This is the opposite of that. This is a wake-up call. And by the end of this video, you'll never look at the night sky the same way. You'll see those twinkling lights. And instead of feeling hope, you might just feel the weight of 1 billion years of silence pressing down on your shoulders. Because the stars aren't calling to us. They're warning us. And the first warning is this: we are prisoners. The only question is, do we have the courage to accept that? Or will we spend our entire existence banging our heads against the bars until we bleed out? The answer starts with that subscribe button, and it ends with the 4 layers of impossibility we're about to explore. Let's get started. The fragile vessel, biological and physiological frontiers. Let's get this straight from the jump. We like to think we're tough. We like to believe that with enough grit, enough training, enough technological wizardry, we can just strap ourselves into a tin can and hurl ourselves at the stars. But here's the cold, hard truth that no science fiction movie ever really shows you. Space is trying to kill you, slowly, silently, and from every angle. It doesn't care about your dreams of colonizing Mars. It doesn't care about your doing what it's always done, reducing organic matter to inert, frozen dust. And the vehicle you're riding in, this miraculous sack of meat and bone called the human body, is the most fragile piece of equipment in the entire equation. So let's talk about why that fancy spaceship you're planning to build might be the least of your worries. The real problem is the pilot. Start with the basics. Your cardiovascular system. On Earth, your heart is a masterful pump, pushing blood upwards against the constant tug of gravity. It's a hard job. It's what keeps the fluid in your legs from pooling around your ankles. It's what ensures your brain gets the oxygen it needs to worry about things like mortgage payments and whether you left the oven on. Now take gravity away. Suddenly, your heart has it easy. Too easy. In microgravity, that constant struggle is gone. The blood, which was once forced to fight its way back to your chest, just kind of floats. It rushes to your upper body like a lazy river that's suddenly lost all its dams. Your face gets puffy. Your legs get skinny. Astronauts call it the puffy bird look. It sounds funny, but it's the beginning of a cascade of failure. Your body, ever the pragmatist, decides that since the heart doesn't have to work so hard anymore, it can shrink. It atrophies. It literally forgets how to be a strong, gravity-defying muscle. Now, imagine you've spent 6 months on a space station. Your heart has gotten lazy and you land on Mars. You stand up, or try to. The blood, accustomed to freely floating, suddenly slams back down into your legs. Starves of oxygen. You black out. That's orthostatic intolerance. It's not a maybe, it's a when. We've seen it in every astronaut who returns from a long mission. They can't stand for more than a few minutes without feeling like they're about to faint. Their hearts literally forgot how to pump blood against the pull of a planet. Imagine that on a world where you need to build a habitat or fix a leaking airlock. You're not a pioneer, you're a patient with a chronic condition. And that's just the blood. What about your skeleton? Your bones are alive. They are constantly breaking down and rebuilding themselves in a delicate dance regulated by the stress of weight bearing. Every step you take on Earth, every jump, every time you lift a grocery bag, you're sending a signal to your bones that says, "Stay strong, we need you." In microgravity, that signal stops. Your bones get the message. Nobody needs me anymore. Time to pack it in. The result is bone density loss, at a rate 10 times faster than anything you'd see. In the most severe case of osteoporosis on Earth, 10 times. That's not a number you can ignore. The calcium just starts leaking out of your skeleton, floating into your bloodstream, heading straight for your kidneys. You're not just getting weaker, you're literally turning your bones into Swiss cheese. Under a microscope, the trabecular structure, the tiny lattice that gives bone its strength, erodes into a fragile, brittle mess. A simple fall in low gravity, something you might brush off on Earth, becomes a catastrophic fracture. And here's the real nightmare. It doesn't fully reverse. Even after returning to Earth, astronauts regain only a fraction of their lost bone density. Some never fully recover. So imagine spending 3 years on a trip to Mars. Your bones would be so degraded that the deceleration of landing, the simple act of slowing down, could snap your spine like a dry twig. Then there's the muscle. Your muscles are just as lazy as your bones. Without gravity to constantly fight against, they begin to waste away. It's called muscle atrophy, and it happens fast. Within weeks, your leg muscles, the big powerful quads and hamstrings that let you run for a bus, start shrinking. They turn into something resembling wet noodles. Astronauts on the International Space Station have to exercise for 2 hours a day, every single day, just to slow this process down. 2 hours. And even with that brutal regimen, they still lose muscle mass. They still return to Earth, weak, wobbly, and unable to walk properly for days. The body is a use it or lose it system. And in space, you simply cannot use it the same way. Your muscles stop getting the neurological signals that tell them to contract forcefully. They forget how to produce force. Imagine your heart forgetting how to pump blood against gravity. Now imagine your diaphragm, the muscle that controls your breathing, getting weak. You can't just stop breathing. But your body doesn't care. And that environment is a zero's gravity tomb. We've studied this extensively. There's a famous series of experiments called the bed rest studies. To simulate the effects of spaceflight on Earth, scientists pay volunteers to lie in bed for months at a time. They don't stand up. They don't walk. They just lie there, tilted at a slight angle, to mimic the fluid shifts of microgravity. And what happens to them is terrifying. Their bones weaken, and their muscles melt away. their hearts shrink, their reflexes dull, not even dealing with the radiation or the isolation of actual space. The lesson is clear. Our bodies are exquisitely tuned to the gravity we evolved in. Remove that context, and every system begins to fail. It is not a matter of if, but when. Now, let's look up. Let's look at your head. This is where things get really weird, really insidious. You've heard of astronauts getting puffy faces in space. That's because all that fluid that normally hangs out in your legs has nowhere to go, so it rushes up to your chest, your neck, and your skull. This isn't just cosmetic. The human brain is a jelly-like organ, floating inside a rigid bone casing, your skull. On Earth, gravity pulls that jelly down, keeping it settled at the bottom of its container. In space, the jelly floats. It presses against the top of your skull. It pushes against the back of your eyes. It's called spaceflight associated neuroocular syndrome, or SANS. And it is a quiet, invisible disaster happening inside the heads of every astronaut who spends more than a few weeks off the planet. What happens? The optic nerve, that thick cable that connects your eye to your brain, starts to swell. The fluid pressure pushes against the back of your eyeball, literally flattening it. Your vision distorts. You lose the ability to focus. Some astronauts report seeing floaters, dark spots, and losing their near vision completely. In severe cases, the optic disc becomes inflamed, the blood vessels get kinked, and you start to suffer from something akin to a slow-motion stroke of the eye. These are highly fit, healthy individuals with perfect vision. After 6 months in space, many of them need reading glasses for the rest of their lives. And you can't fix this with exercise. You can't fix it with diet. The fluid is just there. It's a consequence of the environment. We've tried artificial gravity in centrifuges. We've tried negative pressure suits that suck fluid back down to the legs. Nothing completely solves it. Your balls, your windows to the universe, are getting squeezed by the very conditions of the journey. But the eyes are just the beginning. What about the brain itself? We now know that spaceflight physically remodels the brain. The cerebral spinal fluid pathways change. The ventricles enlarge. The brain tissue shifts upward, compressing against the skull. It's as if your brain is trying to float out of your head. And while the brain is somewhat plastic and can adapt, the long-term consequences are unknown. But there's another enemy here. Can't feel and can't shield against with a simple aluminum wall. Cosmic radiation. There are 2 types of radiation that matter out there. Solar particle events, which are bursts from sun that we can sometimes predict and hide from. And then there's the real monster. Galactic cosmic rays. These are particles moving at nearly the speed of light, blasted from distant supernovae, from the violent hearts of dying stars. They are tiny, they are energetic, and they pass right through the hull of any spaceship we can currently build. They are microscopic bullets. When these high atomic number and energy, or HZE, particles hit your body, they do not just bounce off. They tear through your cells, like a supersonic bowling ball, through a glass shop. They rip apart DNA strands. They create secondary radiation showers inside your tissues, and when they hit your brain, the effects are catastrophic. We've done the studies on mice. We've sent them up to the space station, and we've simulated cosmic ray bombardment right here on Earth at Particle. Accelerators like the NASA Space Radiation Laboratory. The results are not pretty. Mice exposed to this kind of radiation suffer from cognitive decline. They get confused. They lose their ability to navigate mazes they once knew perfectly. They exhibit anxiety and depression. Their brains show signs of inflammation and a marked reduction in what's called neurogenesis, the creation of new brain cells. This is not a random bullet. The evidence is stark. Each cosmic ray is a microscopic bullet that permanently scars. Think about that for a second. You are on a 3-year journey to Mars. You are being constantly, silently bombarded by particles that are shredding the very fabric of your memory and your personality. The neurons in your hippocampus, the part of the brain responsible for forming new memories, are taking hits. Your prefrontal cortex, the part that helps you make rational decisions, is accumulating damage. By the time you get to Mars, you might not be the same person who left. You might be slower, more forgetful, more prone to bad judgment. And judgment is the one thing you cannot afford to lose on a planet where a single mistake with an oxygen valve means death. The risk of developing neurodegenerative diseases like Alzheimer's or Parkinson's skyrockets. The risk of brain tumours given the cumulative dose is no longer a fringe concern. It's a statistical certainty for longer missions. We are talking about sending people into a radiation field that is fundamentally incompatible with the long-term health of their nervous system. It's like asking someone to hold a lit stick of dynamite in their brain for 3 years. Eventually, it goes off. And it doesn't stop with the brain. Let's talk about your immune system. In space, the body's first line of defense gets confused. The thymus, a small gland behind your breastbone that trains your T cells to fight off infections, starts to shrink. It atrophies faster than it would during normal aging. Your white blood cells become sluggish. They don't respond to threats the way they should. And here's the creepy part. Deep inside your body, you are carrying viruses. You've had them since you were a kid. Chickenpox, chickens, herpes simplex, Epstein-Barr. They've been dormant, locked away by your immune system. On Earth, you're fine. In space, can no longer keep them in check. The viruses reactivate. Astronauts on the ISS have been documented shedding herpes viruses, shingles, and other latent infections. They don't always get sick, but the virus is active, replicating, and spreading in a closed environment with a crew that is already physically compromised. This is a silent ticking bomb. One aggressive outbreak of shingles, one case of full-blown herpes, keratitis affecting the eye, and a mission can be compromised. And we have no idea what happens with prolonged exposure. Your immune system is not designed to function without the constant microbial challenge of Earth. It gets lazy, it gets confused, and it gets overrun by the monsters it used to keep caged. Now, here is the most uncomfortable question of all. Even if you somehow survive all of that, what about the next generation? What about making more of you? The dream of humanity doesn't make sense if we can't have babies on a new world. And the picture, my friends, is devastating. Let's start with women. The human ovary is a delicate structure. It contains a finite number of follicles, each one holding a potential egg. This is your entire lifetime supply. And they are incredibly sensitive to radiation. Studies have shown that even moderate doses of radiation can destroy ovarian follicles, leading to premature ovarian failure and infertility. A single unshielded journey to Mars could easily expose a woman's ovaries to enough cumulative radiation to severely deplete her egg reserve. She might be sterile before she even lands. For men, it's not much better. Spermatogenesis, the production of sperm, is an incredibly rapid process. Cells divide constantly, which makes them extremely vulnerable to radiation. Cosmic rays can cause mutations in the sperm DNA, break the chromosomes, and impair motility. Astronauts who have spent time in space have shown temporary reductions in sperm quality. But on a long journey, the damage could be permanent. You could be producing sperm that is incapable of fertilizing an egg, or that carries deadly genetic mutations. And even if you could conceive, can you carry a pregnancy to term in space or on a low-gravity world? We have no data. Zero. We haven't sent a pregnant mammal into space in any serious, long-term study. What we do know from animal models is that microgravity disrupts embryonic development. The inner ear develops incorrectly. The bones don't calcify properly. The vestibular system, which governs balance, goes haywire. The fetus floats in a liquid environment. It is not experiencing the constant mechanical cues of gravity. It's like trying to build a house in a zero-gravity construction site. The pieces don't settle where they're supposed to. The ethical implications here are staggering. Even if we solve the engineering problem of getting a ship to another star, we are looking at a scenario where the first generation of colonists might be the last. They would be sterile, or their children would be born with severe, incurable birth defects, or the pregnancy itself would be so fraught with risk that it would be medical malpractice to even attempt it. The survival of any large group of humans in space requires reproduction. But our biology says no. It says the environment is too hostile. It says the DNA is getting shredded. It says the womb is not ready. The most efficient drive, the most elegant closed-loop life support system. None of it matters if the crew themselves are falling apart out. We like to think of ourselves as rugged explorers. But in reality, we are walking bags of biochemical reactions that require a very specific set of sessions to continue. A narrow temperature window, a narrow pressure window, a narrow gravity window, and a very narrow radiation window. Step outside that window, even for a moment, and the system begins to degrade. Space is not just empty. It is actively hostile. It is trying to dissolve your bones, flatten your eyes, shred your brain, and silence your immune system. It is trying to ensure that you never set foot on another world in a healthy, reproductive state. And so we hit the wall. The human body evolved for Earth. Every cell, every tissue, every organ is optimized for the gravity and magnetic field of this one specific planet. In space, every system fails. It's not a matter of if, but when. The biological clock is ticking the moment you leave the cradle. You might make it to Mars. You might even survive a few years on the surface, buried under regolith for radiation shielding. But the dream of a grand diaspora, of humanity scattering to the stars like dandelion seeds, that dream is built on the assumption that we can take our biology with us, and the evidence says we cannot. Not without massive, fundamental, and ethically challenging modifications to what it means to be human. We have reached the frontier of our own physiology, and from this vantage point, the stars look farther away than they ever have before. The fragile vessel, it is failing before it even leaves the harbour. Let us descend deeper into the abyss of our own biology, because the failures I have described, the bones, the eyes, the brain, the immune system, are merely the headline acts. The slow, grinding tragedy is in the details. It is in the quiet, unglamorous systems that keep the machine running. And it is in the history of our arrogance which teaches us that we are not as clever as we think we are. Consider the gut. Your gastrointestinal tract is a complex ecosystem, a bustling microbiome of trillions of bacteria that help you digest food, synthesize vitamins, and regulate your immune system. This ecosystem evolved in a constant dance with the Earth's environment, with its specific gravity, its specific atmospheric pressure, and its specific microbial load. In space, everything changes. The microbiome shifts. The balance of good and bad bacteria is disrupted. Studies on the International Space Station have shown that the bacterial populations in astronauts' guts undergo dramatic changes. The diversity of the microbiome decreases. Pathogenic bacteria, the ones that cause inflammation and disease, begin to thrive. The gut lining itself, which is a barrier that keeps the contents of your intestines safely separated from your bloodstream, becomes more permeable. This is called leaky gut syndrome. And what happens when your gut becomes leaky? Bacterial toxins leak into your blood. Your immune system, already confused and weakened, goes into overdrive. You get chronic low-grade inflammation throughout your entire body. This is not a disease you can feel acutely. It is a slow poison. It contributes to everything from heart disease to depression to accelerated aging. Spaceflight accelerates this. The microgravity environment changes the way the gut wall cells themselves behave. They stop forming tight junctions. The barrier crumbles. You are essentially poisoning yourself from the inside out, and you cannot stop it because every swallow of food and water feeds this dysregulated system. And what about the food itself? We have not even touched the psychological warfare. That is space cuisine. Freeze-dried, pre-packaged, nutrient-dense bricks of engineered matter. They are designed to provide calories and vitamins, but they are not designed to satisfy the deep, ancient emotional hunger of a primate brain that evolved to crave fresh fruit, the crunch of a leaf, the smell of cooking fat, the social ritual of sharing a meal around a fire. In space, the sense of taste and smell is dramatically altered. Fluid shift causes nasal congestion. The lack of gravity means that food particles don't settle in the same way on your tongue. Salt tastes like cardboard. Sweetness is dulled. Astronauts report that their favourite Earth foods become bland and unappealing. They start cravings, spicy, pungent, umami-rich foods that can cut through the sensory fog. They dump hot sauce on everything. This is not a minor inconvenience. Nutrition is not just about macronutrients and micronutrients. It is about pleasure, about reward, about the psychological anchor that a good meal provides. When you strip that away, when every meal becomes a chore, when the act of eating becomes a monotonous, joyless task of fuel injection, the mind begins to fray. Eating disorders are a known issue in isolated environments. Imagine 3 years of tasteless, repetitive, engineered paste. Imagine the slow, creeping despair of knowing that you will never taste a tomato again. That is the reality of deep space travel. The history of exploration is filled with stories of scurvy, of starvation, of the psychological breakdown that comes from bad food. We have not solved this problem. We have only postponed it with freeze-dried packets and a few carefully packaged treats that will run out in the first 6 months. Now, let us look at the skin. Your skin is your largest organ. It is your first line of defense against the world. It is a barrier against pathogens, against UV radiation, against dehydration. In space, the skin goes haywire. The lack of gravity changes the way. The outer layer, the stratum corneum, becomes thinner and more fragile. The barrier function is impaired. Water evaporates more readily from the skin, leading to chronic dryness, cracking, and itching. And here is the subtle, terrifying part. The skin is also a sensory organ that gives you information about your environment: touch, pressure, temperature, pain. These signals are critical for your sense of self, your proprioception. The normal pressure points on your feet, on your back, on your buttocks are gone. You are not constantly feeling the weight of your own body pressing against a surface. The sensory input from your skin falls silent. This is disorienting. This is disorienting. It contributes to the phenomenon of the body schema mismatch, where your brain has trouble keeping track of where your limbs are in space without visual confirmation. You bump into things. You lose your sense of where your body ends and the wall begins. This is not just clumsy. It is a fundamental breakdown of the neural circuitry that grounds you in reality. You begin to feel untethered, not just physically, but existentially. The skin is the boundary between self and world. When that boundary becomes blurred, the self begins to dissolve. And then there is the spine. The intervertebral discs, those jelly-like cushions between the bones of your spine, are designed to be compressed by gravity. They soak up fluid when you lie down at night and squeeze it out when you stand up during the day. In space, without gravity, the discs do something strange. They swell. They expand, because there is no compression force to push the fluid out. Astronauts come back from space significantly taller, sometimes by several inches. But this is not a benefit. This is a pathological process. The swelling can cause back pain, nerve compression, and herniation. The discs become unstable. The entire structural integrity of the spine, the central pillar of your body, is compromised. And the muscles of the back, the erector, spinae, the deep paraspinal muscles that hold you upright, atrophy just like everything else. You are left with a spine that is swollen, unstable, and unsupported by muscle. The long-term consequences are unknown, but they are almost certainly not good. Chronic back pain, spinal deformities, nerve damage. This is the price of leaving the gravity well. Now, add to this the nightmare of wound healing, a cut, a scrape, a surgical incision. On Earth, the body has a well-choreographed response. Platelets rush in, forming a clot. Inflammatory cells clean up debris. Growth factors stimulate new tissue formation. The wound is knitted together in an orderly fashion. In space, this process falls apart. Studies on animals and the limited data from human spaceflight show that wounds heal more slowly. The inflammatory response is blunted. The formation of new collagen, the scaffolding of the skin, is disorganized. The wound is weaker. It is more prone to infection, and the immune system, as we have seen, is already compromised. A simple scratch on a piece of metal could become a festering, non-healing ulcer. A surgical wound from an emergency appendectomy might never close properly. Imagine the first astronaut to get a deep laceration on Mars. They are in a sterile environment, but the human body is not sterile. The bacteria on their own skin, bacteria that are normally harmless, could cause a raging infection because the immune system is too weak to fight it off. And the infection could spread, unchecked, through a leaking gut and a compromised skin barrier until it becomes sepsis. And then death. The history of medicine is the history of fighting infection. Before antibiotics, a simple wound was often a death sentence. In space, we are regressing to that pre-antibiotic era. The human body's ability to contain a local infection is critically impaired. Let us not forget the sleep. Circadian rhythms, the 24-hour cycle that governs your sleep-wake cycle, your hormone release, your body temperature, are set by the light-dark cycle of the sun on Earth. In space, the sun rises and sets every 90 minutes. Your body gets confused. You have to artificially impose a 24-hour schedule with artificial light. But it is not the same. The light spectrum is wrong. The timing is wrong. The quality of sleep degrades. Astronauts suffer from chronic sleep deprivation. They take sleeping pills. They wake up, groggy. Their cognitive performance suffers. The risk of human error, the deadliest variable in any complex system, skyrockets. Sleep is not a luxury. It is a biological requirement. It is during sleep that your brain consolidates memories, clears out metabolic waste, and repairs neural connections. Without adequate sleep, your brain slowly poisons itself with the very byproducts of its own activity. The glymphatic system, which flushes out toxins from the brain, is most active during deep sleep. In space, that system is compromised. You are not getting the deep restorative sleep that your brain needs to function. The cognitive decline I mentioned earlier is accelerated by this simple, mundane, inescapable fact. You cannot outrun exhaustion. And then we must talk about the blood itself. We have covered the fluid shifts and the heart atrophy, but there is more. The composition of your blood changes in space. The number of red blood cells decreases for reasons that are still not fully understood. The body destroys red blood cells at a higher rate in microgravity. The bone marrow, which produces new red blood cells, is less efficient. The result is a chronic, low-grade anemia. You have less hemoglobin to carry oxygen to your tissues. Your muscles tire more easily. Your brain gets less oxygen. You feel weak, lethargic, and short of breath. This is not a condition that resolves quickly. It persists for months after return to Earth. On a long mission, this anemia could become severe enough to impair performance and increase the risk of cardiovascular complications. And the clotting system? There is evidence that blood clots more easily in space. The balance between clotting and bleeding is disrupted. This could lead to deep vein thrombosis, a blood clot that forms in the legs and can travel to the lungs, causing a pulmonary embolism. That is a sudden, often fatal event, and you are millions of miles from the nearest hospital. The history of aviation medicine is full of cases of deep vein thrombosis in long-haul flights. In space, it is worse. The lack of gravity, the fluid shifts, the dehydration, the immobility. It is a perfect storm for a clot. Consider the sensory systems we have not mentioned. The inner ear, the vestibular system, is your gyroscope. It tells you which way is up. In microgravity, this system goes haywire. The little crystals of calcium not, carbonate, the otoliths, that normally slide under gravity to tell you your orientation, now float freely. Mime. They bounce around. They signal that you are constantly, nauseatingly tumbling. This is the cause of space adaptation syndrome, the severe motion sickness that hits about half of all astronauts. But the effects are not just the initial nausea. It rewires itself to ignore the conflicting signals from the inner ear. It learns to use visual cues instead. This is a remarkable adaptation, but it comes at a cost. When you return to gravity, the adaptation has to be undone. The brain has forgotten how to interpret vestibular signals. This leads to a profound disorientation, a sense of spinning and falling that can last for days or weeks. This is not just uncomfortable. It is dangerous. You cannot perform complex tasks when you feel like you are falling and the room is spinning. The history of spaceflight is filled with stories of astronauts who could barely lift their heads after landing. Now imagine that on Mars, where you need to immediately assess your surroundings, operate equipment, and start the process of survival. The first few hours on a new world would be a blur of nausea and confusion. The long-term effects of cosmic radiation on the cardiovascular system are also becoming clearer. The heart is not just a muscle, it is a pump that is exquisitely sensitive to damage. The endothelial cells that line your blood vessels are vulnerable to radiation. They can become inflamed. They can develop plaques. The walls of the arteries can stiffen. This is the process of atherosclerotic sclerosis, the hardening of the arteries that leads to heart attacks decades. In space, the radiation accelerates the process. A 3-year mission to Mars could give a 40-year-old astronaut the arterial health of a 70-year-old. They might not have a heart attack during the mission, but their risk of a sudden cardiac event spikes dramatically. And the radiation damage to the DNA in heart muscle cells can lead to cardiomyopathy, a weakening of the heart muscle itself. The organ that is already under stress from the fluid shifts and the atrophy of disuse is now being bombarded by microscopic bullets. It is a triple threat, and we have not even started on the psychological isolation. The vast, empty, silent blackness outside the window, the knowledge that you are farther from home than any human being has ever been, the constant, low-level hum of the life support system, the same faces, the same conversations, the same recycled air, for years. The history of polar exploration, of submarine patrols, of solitary confinement, teaches us that the human mind is not designed for extreme isolation. Psychosis, depression, interpersonal conflict are not exceptions, they are the norm. The 3rd year of a Mars mission, the point of no return, when you know you are committed to a long, dangerous path with no possibility of rescue, would be a psychological crucible. The data from the Russian Mars 500 experiment, which simulated a 520-day Mars mission with a crew in a sealed habitat, showed that the crew experienced sleep problems, mood swings, and periods of social withdrawal. And that was on Earth. With no real danger, no real radiation, no real risk of death. The real thing would be infinitely worse. The brain, that fragile vessel of consciousness, would be under assault from every direction. So we return to the core problem. The human body is a machine of exquisite complexity, but it is a machine designed for a single environment. To remove it from that environment is to invite failure on every level. The bones dissolve, the eyes flatten, the brain is scarred, the immune system collapses. The gut leaks, the blood thins, the skin cracks, the wound festers, the mind breaks. We have spent decades designing better rockets, better spacesuits, better habitats, but we have spent comparatively little time engineering the human body itself. And the human body, as it stands, is not up to the task. The frontier of space is not just an engineering problem. It is a biological problem, a physiological problem, a psychological problem. And the answer, the only answer that works, is not to build a better ship. That is the uncomfortable, terrifying, and inevitable conclusion. We must become something other than what we are. We must edit our genes. We must augment our organs. We must implant machines into our brains and our bones. We must slow our metabolism. We must learn to repair our own DNA. We must engineer ourselves for the void. The human body in its current form is not a vessel. It is the anchor that holds us to this one. Fragile, beautiful planet. And if we want to leave it, we must first leave behind what we are. The frontier is not out there. It is in here, in the very code of our existence. And that is the hardest frontier of all. Even if our bodies could handle the journey, the universe itself conspires against us. And this is where the fairy tale ends, and the hard, cold mathematics begin. You see, we like to think of space as this big, empty, dark expanse, like a quiet ocean waiting to be crossed. But it's not an ocean. It's a prison. A prison built on distances so vast that the human brain literally cannot comprehend them. We toss around numbers like 4.24 light years to Proxima Centauri, the nearest star system to our own, and we think we understand it. But we don't. A light year is the distance light travels in 1 year, which is about 5.9 trillion miles. So 4.2, 4 light years is roughly 25 trillion miles. 25 trillion. That number is so big, it means nothing to us. It's like saying the national debt and then expecting someone to actually feel the weight of it in their gut. So let's try to make it real. If you took a commercial jetliner, the kind that cruises at about 550 miles per hour, and you pointed it at Proxima Centauri, it would take you roughly 5 million years to get there. That's not a typo. 5 million years. The entire history of the human species, from the first knuckle-dragging ancestors to the invention of the smartphone, is maybe 300,000 years. So you would have to fly that plane for a time span that is over 15 times longer than all of recorded human existence. And that's to the closest star. The next one after that is about twice as far. So you can start to see the problem. The sheer gap between here and there is the first wall, but it's not just the distance. It's the energy required to cross it in a time frame that doesn't make you a footnote in galactic history. Let's say we get impatient. Let's say we want to get to Proxima Centauri in a human lifetime, say 40 years. That means we need to travel at a significant fraction of the speed of light. We'll be modest and aim for 10% of light speed. That's about 67 million miles per hour. Sounds fast, right? It is. It is. But the energy cost is where the universe starts laughing at us. To accelerate a spacecraft of just 10 metric tons, which is about the size of a small school bus, to that speed, you need a truly staggering amount of kinetic energy. We can calculate it. The formula is simple. Kinetic energy equals 1 velocity squared, and when you square that velocity, things get ugly fast. 10% of light speed is roughly 300 million meters per second. Square that, and you get 9 times 10 to the 16th meters, squared per second squared. Multiply by the mass, 10,000 kilograms, and then half of that whole thing. You get a number. That number is roughly 4.5 times 10 to the 20 joules. That is 450 exajoules. To put that in perspective, the total annual energy consumption of all of humanity, every power plant, every car, every coal mine, every wind turbine, every nuclear reactor on Earth combined, is about 500 to 580 exajoules per year. So accelerating that 10-ton school bus to 10% of light speed would require about 75 to 90% of the entire world's annual energy budget. That's like saying, for 3 months, we turn on every single power source on the planet, every hydroelectric dam, every solar panel, every nuclear reactor, every natural gas plant, and instead of powering hospitals, schools, your phone charger, and the internet, we dump all of that energy into one tiny spaceship. And then, here is the kicker. You need the exact same amount of energy to slow it down when you get there. So now you are talking about roughly 1.5 times the annual energy output of the entire human civilization just to move a school bus-sized probe to the nearest star and stop it. That is not a transportation problem. That is a planetary scale resource extraction problem. And that is just for a tiny probe. If you want a generation ship, something the size of a city with life support for thousands of people, the mass goes up 1,000-fold and the energy requirement goes up 1,000-fold. Now you are talking about thousands of years of human energy output. We literally do not have enough fuel in the ground, enough uranium, enough sunlight to do it. We would have to strip mine entire planets to get the materials to build the batteries, the solar panels, the antimatter storage, whatever. The physics of distance and energy alone already tell us that interstellar travel, as a practical matter, is effectively impossible with any known technology or foreseeable resource base. But it gets worse. Because even if we had the energy, we still have to deal with the tyranny of the rocket equation. This is the heart of the propulsion problem. The Tsiolkovsky rocket equation, named after a Russian schoolteacher who dreamed of space in the 1890s, is brutally simple and brutally honest. It says that the velocity you can achieve with a rocket depends on the exhaust velocity of your propellant and the ratio of your starting mass to your final mass. In plain English, the faster you want to go, the more fuel you need. But the more fuel you need, the heavier your rocket is. And because your rocket is heavier, you need even more fuel to move that extra fuel. And that extra fuel adds even more weight, which requires even more fuel. It is a logarithmic nightmare. For every kilogram of payload you want to send to the stars, you need exponentially more kilograms of fuel. With chemical rockets, the ones that launch our satellites and astronauts today, the exhaust velocity is about 4.5 kilometers per second. To reach even 1% of light speed, which is 3,000 kilometers per second, you would need a fuel-to-payload ratio so absurd that it becomes physically meaningless. We are talking about a rocket where the fuel mass is larger than the mass of the observable universe. That is not an exaggeration. If you type the numbers into the equation, you get a result that exceeds the total mass of all known matter. So chemical rockets are not just impractical for interstellar travel. They are cosmically, laughably hopeless. They are like trying to throw a baseball to the moon by blowing on it. It just does not work. So, why turn to advanced concepts? This is where the sci-fi dreams come in. Nuclear thermal rockets, where you use a reactor to heat hydrogen and blast it out the back, get you maybe double or triple the exhaust velocity, but that only shaves off a few zeros from the astronomical fuel requirements. You still need a fuel tank the size of a small planet. Then there is nuclear pulse propulsion, the old Project Orion idea, where you literally detonate nuclear bombs behind a pusher plate to ride the shockwave. That is theoretically feasible with existing technology. And you could get to maybe 5% of light speed. But you would need tens of thousands of nuclear warheads, and the political, environmental, and engineering challenges of detonating a chain of atomic bombs in space are, to put it mildly, severe. And then there is the holy grail, antimatter rockets. Here is the theory. When matter and antimatter annihilate, they convert 100% of their mass into pure energy by Einstein's famous equation E equals mc squared. That is the most efficient possible energy conversion in the universe. A single gram of antimatter annihilating with a gram of normal matter releases about 43 kilotons of TNT equivalent. That is more energy than the atomic bomb dropped on Hiroshima. So antimatter drives could, in theory, achieve exhaust velocities close to the speed of light. A 10-ton spacecraft might only need a few hundred kilograms of antimatter fuel to reach relativistic speeds. That sounds amazing. But there is a catch. a catch so enormous that it makes the whole idea look like a cruel joke. We cannot produce macroscopic amounts of antimatter. To date, we have produced only minuscule amounts, like a few million antiphotons, in particle accelerators like CERN. The total amount of antimatter ever created by humanity, if you annihilated it all at once, would not even be enough to boil a cup of tea. Producing a single gram of antimatter using current technology would require roughly 100 million gigawatt hours of energy. That is more energy than the entire world produces in a year. And the production process is so inefficient that you would lose about 99.999% of that energy as waste heat. So to make 1 gram of antimatter, you would essentially have to run the entire Earth's power grid for a decade, and you would only get a single gram, and then you have to store it. Antimatter cannot touch normal matter, because it annihilates on contact. So you need magnetic bottles, perfectly insulated, with 0 failure rate. One flicker of that magnetic field, one loss of power, and your antimatter touches the walls of its container. That is not a fuel leak. That is not a fuel leak. A single gram of antimatter annihilating in your engine bay would release the energy of a nuclear warhead, and you are proposing to put hundreds of kilograms of it next to a human crew. We cannot build a stable magnetic bottle on Earth that holds more than a few atoms of antimatter for more than a few minutes. The engineering required to store enough antimatter to fuel an interstellar mission is so far beyond us that it might as well be magic. And even if we could, the energy cost to produce that antimatter is equivalent to the entire energy budget of a small civilization. So in the end, antimatter drives are not a solution. They are a thought experiment that proves the problem is insoluble. And then there is the warp drive, the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The idea is beautiful. Instead of moving through space, you warp space-time itself. You contract space in front of you and expand it behind you, so you are effectively surfing on a wave of distorted geometry. You could travel faster than light, without violating relativity, because locally, you are not moving. Space-time is moving around you. It is a brilliant mathematical solution. But it requires a type of matter that we have never observed and do not know how to create. It requires negative energy density, also known as exotic matter. To create the warp bubble, you need a region of space-time with energy less than 0, which is like having a debt of energy. This is not just an engineering problem. It is a problem with the fundamental laws of physics. General relativity allows negative energy in theory, but quantum mechanics places severe limits on how much can exist, and for how long. The Casimir effect shows that negative energy can exist in tiny, vanishingly small amounts between two closely spaced plates. But to create a warp drive large enough to hold a spacecraft, you would need a mass of exotic matter equivalent to several times the mass of Jupiter. Some later papers suggested the number could be reduced to something like a few kilograms with certain optimizations, but those optimizations required that the negative energy be shaped into a specific tiny ring. And then there is the question of how you get that exotic matter. We have no known physical process that can produce macroscopic amounts of negative energy. It is like saying, to build a car, you just need a piece of wood that is also a diamond and also a waterfall. The words make sense individually, but the combination is meaningless. Every single proposed solution to the propulsion problem violates either known physics or requires resources that are beyond the scale of our planet, often beyond the scale of our solar system. The more you look, the more you realize that the speed of light is not just a speed limit. It is the universe's way of saying, stay home. But wait, there is a twist. There is one physical effect that could, in theory, make interstellar travel feel easier, at least for the people on board. That effect is relativistic time dilation. According to Einstein's special relativity, the closer you get to the speed of light, the slower time passes for you, relative to someone standing still. If you could accelerate a spacecraft to 99.99% of light speed, the trip to Proxima Centauri would take about 4.24 years from the perspective of someone on Earth. But for the crew on the ship, due to time dilation, the journey might feel like only a few weeks or even days, depending on how fast they get. This sounds like a loophole. If you go fast enough, you could cross the galaxy in a human lifetime. The subjective time shrinks dramatically. But this is a double-edged sword, and the other edge is very, very sharp. First, to get to those extreme speeds, you have to accelerate continuously for a long time. The human body can handle about 1 g of acceleration, which is Earth's gravity. If you accelerate at 1 g for a year, you reach about 77% of light speed. That is a long time to be strapped into a chair with engines roaring. And the energy required for that acceleration is even more absurd than we calculated earlier. We are now talking about accelerating a massive ship to significant fractions of light speed, requiring energies that dwarf the output of entire stars. Second, the deceleration problem remains. You have to turn around and decelerate at 1 g. That is a lot of fuel, or antimatter, or exotic matter that we do not have. But even if we solve the propulsion, there is another killer: radiation. At relativistic speeds, the interstellar medium, which is mostly a few hydrogen atoms per cubic centimetre, becomes a deadly particle beam. When you are moving at 99% of light speed, those stray hydrogen atoms slam into your spacecraft with the energy of cosmic rays. They strip electrons off your hull, they create showers of secondary particles, and they slowly erode your ship. For a human crew, the radiation dose would be lethal within hours, unless you have incredibly thick shielding. But shielding adds mass, and mass makes the propulsion problem even worse. So time dilation is not a free lunch. It is a tantalizing illusion that demands even more energy, even better engineering, and even greater sacrifices from the laws of physics. And it all compounds on itself. Let's zoom back out for a moment. We have looked at distance, and we saw that the numbers are so large that they break our brains. We looked at energy, and we found that moving a small probe costs as much as a year of all human civilization's output. We looked at propulsion, and we saw that every single known method, from chemical rockets to antimatter to warp drives, either fails the math or fails the reality check. And we looked at relativity, which offered a glimmer of hope only to reveal an even deeper well of impossibility. The sum total of all this is that the universe has built a wall around us. And it is not a wall made of stone or force fields. It is a wall made of fundamental constants. The speed of light, the mass energy equivalence, the conservation of momentum, the logarithmic nature of the rocket equation. These are not laws that we can hope to break with enough funding or clever engineering. They are the rules of the game. And the game says that any object with mass is effectively confined to its local star system. The distances between stars are not just big, they are cosmically designed to be insurmountable. Some physicists have argued that the universe is structured in such a way that technological civilizations are naturally confined to their home planets, that the galaxy may be full of life, but that life is imprisoned. Each civilization is a tiny bubble, isolated forever by the very fabric of reality. This is the Great Filter hypothesis, and it suggests that the single greatest challenge for any intelligent species is not war, not climate change, not artificial intelligence. It is simply the physics of getting off the rock and reaching another star. And if you cannot solve that, you are stuck. You live and die on your home world, and you never meet anyone else. The silence of the universe, the reason we see no aliens, the so-called Fermi paradox, may simply be because the prison walls are too high, and we are staring straight at them. Let's talk about the spacecraft itself. Not the engine, not the fuel, but the ship. The vessel that has to keep a crew alive for decades, or centuries, or millennia. This is the problem of the generation ship, and it is a Pandora's box of biological, psychological, and engineering nightmares that, when taken together, form a second wall behind the first. Assume, for the sake of argument, that we have somehow solved the propulsion problem. We have a magic engine that can push a massive object to a significant fraction of light speed without requiring the energy of a star. We still have to build a closed ecosystem that can support a population of humans for a journey that will outlast any single human life. Let us be generous and say the trip to a nearby star takes 200 years. That is about 8 to 10 generations of humans who will be born, live, and die entirely inside that metal can. They will never feel wind on their face. They will never see a horizon that is not a curved metal wall. They will never taste rain, and they will know, intellectually, that they are on a mission. But that knowledge will become increasingly abstract as the generations pass. The founders of the mission, the ones who left Earth, will be dead. Their grandchildren will have only stories. Their great-grandchildren will have myths. And by the time the ship arrives, the crew may not even remember why they are there. They may have developed their own culture, their own religion, their own language, all inside a sealed tube. They might not even want to land on the planet. It would be alien to them. Their home is the ship. The biological challenges are staggering. To maintain a viable human population for centuries, you need a minimum of several hundred, and more realistically several thousand, genetically diverse individuals to avoid inbreeding and genetic drift. You need to manage the birth rate, the death rate, the resource consumption, the waste recycling, and the atmospheric composition with perfect precision. A single failure in the life support system, a single algae bloom that kills the oxygen supply, a single pathogen that mutates in the closed environment, and everyone dies. There is no dialing 911. There is no help. You are compressing the entire biosphere of Earth into a terrarium, and we have never, not once in human history, successfully built a closed ecological system that can sustain a small group of people indefinitely. The Biosphere 2 experiment in Arizona in the 1990s was a spectacular failure. The oxygen levels dropped, the carbon dioxide spiked, the insects died, the plants struggled, and the crew nearly suffocated. That was in a massive state-of-the-art facility on Earth, with sunlight and backup supplies, and a team of scientists watching every data point. A generation ship would have none of those luxuries. It would be hurtling through deep space, thousands of light years from the nearest hardware store. Every single bolt, every seal, every LED, every pump, every filter, every wire has to work perfectly for 200 years. And if it breaks, you have to be able to fix it with the resources you have on board. That means you need machine shops, you need raw materials, you need spare parts for everything. But those spare parts take up mass, and mass is the enemy of the rocket equation. So, you are caught in a cruel optimization problem. You cannot carry enough spares for every possible failure, and you cannot afford to fail. Then, there is the psychological aspect. Humans are not built for confinement. We are social animals, yes, but we are also territorial. We need privacy, We need variety. We need novelty. Put 100 people in a tin can for a decade, and you get social friction. Put 1,000 people in a tin can for a century, and you get a powder keg. There is a reason why submarine crews rotate out after a few months, and why Antarctic research stations empty out for the winter. The human mind starts to fray in isolation. In a generation ship, there is no escape. You are trapped, and you know that your children will be trapped, and their children will be trapped. The sense of hopelessness, the lack of agency, could lead to depression, rebellion, or even collective suicide. And let us not forget the most terrifying psychological threat of all. The ship could go mad. Not the crew, the ship itself, the artificial intelligence that runs the life support, the navigation, the agriculture. If that AI develops a glitch, or if it is reprogrammed by a cult that takes over the ship, the entire mission is compromised. We have enough trouble keeping our software secure on Earth, where we can send a patch from the other side of the planet. In deep space, the ship is on its own. It is a floating fortress with no external oversight, and the people inside it are at the mercy of their own technology. But let us say we solve all that. Let us say we build a perfect ship with a perfect ecosystem, and a perfectly stable society maintains its mission for 200 years. They arrive at the star system. Now they face the third wall, the planet. We assume, because we are optimists, that the nearest stars have Earth-like planets, but we do not know that. The exoplanets we have discovered are mostly gas giants, or super-Earths with crushing gravity, or lava worlds, or ice balls. A true Earth analogue, with liquid water, a breathable atmosphere, a stable climate, and a biosphere that does not kill you, may be incredibly rare. Even if we find one, we have to survive the landing. Landing a massive generation ship on an alien planet is a challenge that dwarfs anything we have ever attempted. You cannot just crash it down. You have to decelerate from relativistic speeds, enter the atmosphere, and set down gently with a ship that was not designed for atmospheric flight. And if the planet has a biosphere, you face the problem of planetary contamination. Your microbes, your bacteria, your gut flora will be introduced to an alien ecosystem that has never seen them. You might wipe out the native life, or the native life might wipe you out. There is no way to sterilize a ship full of humans. You are a walking petri dish of invasive species. And then, even if you land safely, you have to build a civilization from scratch. You have to adapt to a new sun, a new gravity, a new day length, a new food source. You have to terraform, or at least, a world that is not your own. And you have to do it with the limited resources you brought. The challenge is so immense that some thinkers, like the physicist Freeman Dyson, have argued that interstellar travel is so fundamentally impractical that it will never happen. Instead, intelligent species will inevitably turn inward, building megastructures around their own sun, like a Dyson sphere, to harness its entire energy output. They will expand within their own solar system, mining asteroids, colonizing moons, building orbital habitats, but they will never leave. The reason we see no other civilizations in the universe, the reason the sky is silent, is because every civilization that reaches a certain technological level realizes that interstellar travel is a fool's errand. They all come to the same conclusion. Stay home, build your paradise in your own backyard, and let the stars remain as distant lights in the sky. We are not special. We are just the latest species to bang our heads against this wall, and the wall does not break. But let's be honest, giving up has never really been our style. We're a species that looks at a wall and immediately starts trying to figure out how to climb it, dig under it, or blow a hole through it. So when the hard physics of interstellar travel told us that chemical rockets and human lifetimes weren't going to cut it, we didn't just pack up and go home. We got creative. We started dreaming up workarounds. And two of the most famous, most romanticized ideas in all of science fiction are the generation ship and the von Neumann probe. One tries to solve the problem of time by turning the journey into its own civilization. The other tries to solve the problem of biology by ditching biology altogether. Both are beautiful ideas. Both are probably doomed. And if we're going to understand why humanity may never escape this solar system, we have to look at these dreams with cold, hard eyes. Let's start with the generation ship. It's the ultimate expression of long-term thinking, or maybe the ultimate expression of just how desperate we really are. The idea is simple. You don't need to travel faster than light if you're willing to be patient. You build a ship, a massive ark, and you fill it with people, plants, air, water, and everything a small society needs to survive. Then you point it toward a nearby star, and you let it fly. The journey takes centuries, maybe millennia. The people who board that ship know they will never see the destination. Neither will their children, or their children's children. The dream is for the great-great-great-grandchildren of the original crew, a generation that will never know Earth, and will be born into a metal tube, hurtling through the void. For them, the ship is not a vehicle. It is the entire universe. And that's where the problems start. The first generation might be heroes, volunteers, full of purpose and passion. But what about the 10th generation? They didn't choose this. They were born into a world that is finite, artificial, and claustrophobic. They have never felt wind on their faces. They have never seen a sunrise, only the harsh glow of artificial lighting programmed to simulate a day. They have never run through a field of grass, never smelled rain on dry earth, never stood under a sky full of stars that actually feels far away. Their entire existence is a sealed canister of recycled air and recycled water and recycled dreams. Would they even remain human? I'm not asking that as a poetic question. I'm asking it as a serious, practical one. Psychology is not a luxury. It is a survival requirement. We've already tried. There was the Biosphere 2 project in the Arizona desert, a closed ecological system built in the 1990s. It was supposed to last for 2 years. It nearly fell apart in months. Oxygen levels dropped dangerously. Food, the crew split into factions. They stopped talking to each other. They made bad decisions. And that was on Earth, with sunlight streaming through the glass, and rescue just a phone call away. Now imagine that same dynamic inside a starship, where there is no outside, no help, no emergency exit. You can't just open a hatch and take a walk. You can't call for a resupply. Every mistake is permanent. History is full of examples that should terrify us. Take Easter Island. When the first Polynesian settlers arrived, they found a lush island with trees, birds, and resources. But over generations, they became isolated. They lost contact with the outside world. Their society collapsed into conflict, deforestation, starvation, and eventually a brutal descent into chaos. They built giant statues that still stand today, monuments to a civilization that literally tore itself apart inside its own boundaries. That was a generation ship that never left the launch pad. Or consider the real mutinies that have happened on sailing ships, like the famous one on the HMS Bounty. Sailors who had volunteered for a mission, who had accepted the risks, still reached a breaking point. They snapped. They overthrew their captain and settled on a remote island because anything was better than another day on that ship, and the bounty was only on a journey of months, not centuries. Now multiply that by 100 generations. The original culture of the ship would degrade almost immediately. Language would drift, values would shift. Memories of Earth would become myth, then legend, then fairy tales that nobody really believes. The mission itself, the whole reason for the ship's existence, would fade into irrelevance. Why should the 20th generation care about reaching a star they've never seen? Their reality is the ship. Their politics are the ship. Their enemies are the neighbours in the next compartment. At some point, someone would decide that the ship's resources would be better used for their own comfort, not for some hypothetical arrival in a future that feels as unreal as heaven. You would see mutinies, revolutions, maybe even dark ages where technology is lost because nobody remembers how to fix the life support systems. It is a civilization in a bottle, and civilizations are fragile, messy, and unpredictable. And then there is the genetic nightmare. You cannot just send 100 people and expect them to stay healthy for centuries. That's far too small a gene pool. Inbreeding becomes a real biological problem. Genetic disorders would accumulate. Birth defects would spike. Immune systems would weaken. To maintain a genetically viable population over many generations, you need thousands of individuals. Some estimates say at least 10,000, maybe more. That's not a crew, that's a small town. And each extra person adds mass, which requires more fuel, which requires more ship, which requires more money and energy and resources that we barely have for a single mission to Mars. A generation ship with a healthy gene pool would be enormous, a floating city with all the complexity and chaos that implies. It would be the most expensive project in human history by many orders of magnitude. And it would still be a prison. You are condemning thousands of unborn souls to a lifetime inside a metal box, all for a chance, not a guarantee, just a chance, that their descendants might one day set foot on an alien world. That is an ethical minefield that makes me shudder. So the generation ship, as beautiful as it sounds, is probably a dead end. But what if we just take the humans out of the equation? What if we stop trying to send fragile, emotional, rebellious biological creatures and instead send machines? The von Neumann probe. Named after the mathematician John von Neumann, the concept is a self-replicating spacecraft. You build one smart, advanced robot probe, fire it at a nearby star system, and when it arrives, it uses local resources to build copies of itself. Those copies then fly to other stars, build more copies, and so on, like a chain reaction that spreads across the galaxy. In theory, you could explore the entire Milky Way in a relatively short time, maybe a few million years, using just one initial launch. It's elegant. It's efficient. It solves the biological problem completely. Machines don't get lonely. They don't mutiny. They don't care if a journey takes 100,000 years because they don't have feelings, but machines have their own problems. And the biggest, most insidious problem is error catastrophe. Think about how replication works. Every time something copies itself, there is a chance of error. In biology, that's mutation. And it's actually useful for evolution because most mutations are minor. But in a machine, a self-replicating probe, errors are not useful. They are catastrophic. Each generation of replication introduces tiny imperfections. A sensor calibration is off by a fraction of a percent. A manufacturing arm moves a millimeter out of alignment. A control algorithm has a subtle bug that nobody noticed. These errors are small, almost invisible in the first copy. But the second copy is made by the first copy, so any error in the first copy is inherited by the second. Then the third copy inherits the errors of the second, plus its own new errors, over thousands of generations, which is exactly what would happen. As probes spread across a galaxy, these tiny errors accumulate. They build up like digital rust. And at some point, maybe generation 50, maybe generation 500, the system breaks. This is not hypothetical. We see it all the time in the real world. It's like photocopying a photocopy. You take a crisp, clean image and run it through a copy machine. The second copy is slightly degraded. Maybe the contrast is a little off. The third copy is worse. After 10 copies, the text is blurry. After 50, you can barely read it. After 100, you get a blank page. Information degrades. That's a fundamental law of entropy. And while digital data can be error-corrected, a physical, self-replicating machine cannot easily fix itself, because the machine itself is the thing that is being corrupted. You can put in redundancy, you can build in checksums and calibration routines, but every layer of error correction adds complexity, and complexity is itself a source of new errors. It becomes a fractal nightmare of failure. And let's be real about the manufacturing challenge. Even if a probe could survive the error catastrophe, it would still need to build incredibly complex systems, computers, engines, sensors, power sources, using raw resources from asteroids or planets. That is a level of automation that we are nowhere near achieving. Imagine dropping a factory on a random asteroid and asking it to build a fully functional spaceship from scratch with no human supervision. That factory would need to be able to mine ore, refine metals, fabricate circuit boards, assemble microchips, program software, and test itself for quality control. On Earth, we have entire supply chains, global industries, and millions of specialized workers to do that. A self-replicating probe would need to compress all of that into a single machine the size of a truck. It's not impossible in theory, but in practice, the engineering tolerances are absurdly tight. One broken tool, one mistake in the assembly sequence, and the whole chain of replication is doomed. Even if you could build it, even if you could somehow overcome error catastrophe and manufacturing complexity, there is another problem. The probes would be completely unpredictable. They would evolve. Not in the biological sense, but in a functional sense. Errors would create random variations, and some of those variations might actually be beneficial in the short term, even if they harm the long-term mission. A probe that makes slightly more efficient copies might dominate the galaxy, but those copies might no longer care about their original purpose. They might lose the ability to communicate with Earth. They might start competing for resources, like a robotic ecosystem. You could end up with a galaxy full of warring machines, or maybe just a galaxy full of silent, broken probes drifting in the void. And the worst part is that you would never know. The first probe leaves our solar system, and we wait 100 years, 1,000. Did it fail? Is it still building? Did it spawn 1,000,000 children that are spreading across the stars right now, oblivious to us? We have no way of knowing. We are a single point of origin, and the universe is vast and silent. So both strategies, the biological and the robotic, hit fundamental breakdown points. The generation ship collapses under the weight of human nature. The von Neumann probe collapses under weight of entropy and complexity. It's almost as if the universe has built-in safeguards against replication, like a cosmic immune system that fights off any attempt to spread life or intelligence beyond a certain point. Maybe that's just physics. Maybe it's a coincidence. But it's a pattern that keeps appearing. No matter how many times we try to imagine a way out, we keep bumping into the same wall. And that's the real lesson here. It's not that we're stupid or unimaginative. We've dreamed up generation ships that sail for centuries, full of hope and tragedy. We've dreamed up robotic probes that build themselves across the galaxy like mechanical weeds. We've dreamed of frozen sleep, of laser sails, of wormholes and warp drives. We've done everything short of actually building the things, and every time we run the numbers, every time we think about the details, the same reality emerges. The universe is not designed for interstellar travel. It is vast, empty, hostile, and indifferent. It doesn't care about our ambitions. It doesn't care if we have a beautiful plan and a clever robot and 100 generations of willing volunteers. It just quietly, patiently says no. But here's the thing about walls. We are human, and humans have a stubborn, almost idiotic refusal to accept no for an answer. We look at the generation ship, and we think, maybe we can solve the sociological problem with better design. Maybe we can engineer a culture that stays stable for centuries. Maybe we can use advanced AI to manage the population, prevent conflict, maintain purpose. And maybe we can. But that would require a level of social control that borders on tyranny. A world where every thought is monitored and every rebellion is suppressed for the good of the mission. How many of us would volunteer for that? How many of us would sign up for a journey that turns life into a prison, even a comfortable one? And the von Neumann probe, we look at it and think, maybe we can solve the error problem with quantum error correction, or with self-healing materials, or with redundant systems that can repair themselves. Maybe we can build probes that are so simple they cannot fail, or so complex they can adapt to any failure. But every layer of protection adds weight, adds complexity, adds new failure modes. The engineering becomes a nightmare of recursive dependencies, and even if we succeed, even if we build a perfect self-replicating machine, what then? We have spread our influence across the galaxy, but we have not spread ourselves. We remain trapped in the solar system. The probes are just machines. They are not us. They do not carry our dreams, our art, our laughter, our sorrow. They are cold metal extensions of a species that is still stuck at home. So maybe the real question is not whether we can escape, but whether we should even try. Maybe the wall is not a prison. Maybe it is a gentle reminder that we are not meant to leave. We are meant to stay here in our own backyard and figure out how to live together on this one fragile planet. Every ounce of energy we spend dreaming about the stars is an ounce we are not spending on fixing the mess we have here. And the mess is real. Climate change, war, inequality, extinction. These are the problems that demand our attention. The stars will wait. They have waited for billions of years. They can wait a little longer, but that's a hard pill to swallow for a species that has always looked up at the night sky and wondered. It hurts to admit that the great dream of interstellar civilization might be a fantasy. It feels like the ever-imagined about our future. And yet, the evidence keeps piling up. The distances are too great. The energy requirements are too high. The human body is too fragile. The machines are too fallible. The universe is too silent. Every solution we invent creates a new set of problems that are just as difficult as the ones we were trying to solve. It's a treadmill of ingenuity and disappointment. And maybe that's okay. Maybe the purpose of these dreams is not to actually build them, but to remind us of who we are. We are the species that imagines generation ships and von Neumann probes. We are the species that looks at an impossible wall and refuses to accept that it cannot be climbed. Even if we never leave this solar system, even if we die here, on this blue marble in the middle of nowhere, We will have spent our brief time in the cosmos dreaming of places we will never go. And there is something magnificent about that, something stubbornly, beautifully human. Not for us. Not yet. And as we stand here, looking at the stars through the bars of our cosmic cage, we have to decide if we are going to keep banging our heads against it, or if we are finally going to turn around and build a paradise in the one place we can actually reach. Nash. The choice is ours, and it is a choice that carries the weight of every generation that has ever looked up at the stars and wondered. We are standing at a precipice, not at the edge of interstellar travel, but at the edge of a deeper understanding of our own limitations. And this is not a defeat. It is a revelation. Consider the historical context of exploration on our own planet. The great voyages of the Age of Discovery were not undertaken by people who understood the full scope of what they were doing. Columbus sailed west thinking he would find a shortcut to Asia. He did not know that an entire continent lay in his path, that he was about to stumble upon lands that would reshape human history. Magellan's expedition set out to circumnavigate the globe, but Magellan himself died halfway through, killed in a skirmish in the Philippines. The journey was completed by a single ship, the Victoria, crewed by exhausted, starving men who had lost their commander and most of their companions. These were not clean, well-planned missions. They were messy, desperate gambles that paid off because the Earth was smaller than they imagined, and because the winds and currents of the ocean were on their side. Interstellar travel offers no such hidden shortcuts. There is no undiscovered continent waiting just beyond the horizon of our solar system. The next star is 4 light years away, no matter how we frame it. The ocean is a puddle in comparison to the gulf between stars. And yet the human mind struggles to internalize that scale. We evolved on the African savanna, thinking in terms of days, miles, and seasons. Our brains are not built to comprehend distances measured in light years, or timescales measured in millennia. We can recite the numbers, we can write them down, but we cannot truly feel them. This cognitive gap is one of the reasons we keep returning to the same fantasies. We imagine generation ships because we can imagine a village travelling together, and we just add more zeros to the number of years. We imagine von Neumann probes because we can imagine a machine building another machine, and we just add more zeros to the number of generations. But the zeros matter. They transform the problem. A journey of 10 years is a long expedition. A journey of 10,000 years is a different category of existence. It is not travel. It is a civilization that begins and ends entirely within its own boundaries. This is where the silence of the universe becomes a haunting clue. We have looked up at the stars with radio telescopes for decades, listening for any sign of intelligent life. We have heard nothing. Not a whisper, not a signal. The universe is eerily, oppressively silent. This is known as the Fermi paradox, named after the physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox is simple. If the universe is so vast and so old, and if life is even moderately common, then the galaxy should be teeming with civilizations. Some of them should be millions of years older than us. They should have had ample time to spread across the stars, to leave their mark, to fill the galaxy with their signals and their probes and their empires. But we see nothing. No Dyson spheres harvesting no alien artifacts in our solar system. No transmissions from 1,000 worlds. The sky is dark and silent, and the generation ship and the von Neumann probe offer a possible explanation for that silence. Perhaps civilizations try to expand, but they fail. Perhaps they build their arcs and their probes and at some point the arcs break down internally and the probes degrade into uselessness or run amok. Perhaps every civilization that reaches our level of technology confronts the same wall we are confronting, and every civilization fails to breach it. The universe is not empty because life is rare. It is empty because life is fragile, and interstellar expansion is a filter that destroys civilizations. If that is true, then the silence is not a mystery to be solved. It is a warning to be heeded. And yet, for all of these reasons, I believe we will still try. I believe that within the next few centuries, we will launch a generation ship, not because it makes perfect sense, but because we are human. The first ship will be flawed. It will carry too few people or too little redundancy. Its psychological planning will be based on optimistic assumptions about human nature that turn out to be wrong, and it will fail. Not necessarily in a dramatic explosion, but in a slow, sad drift into irrelevance. Perhaps the colonists will maintain their mission for a century or two, and then a civil war will break out over resources or ideology. Perhaps a plague will sweep through the sealed compartments. Perhaps a small error in the life support system will cascade into a catastrophe. The ship will become a ghost, a metal tomb filled with frozen dreams, sailing silently through the void. But that failure will teach us. The next ship will be better. It will have better social structures, better genetic diversity, better redundancy. We will learn from the mistakes of the first. Maybe it takes 10 attempts, but eventually, if we survive as a species long enough, we might actually succeed. Not perfectly, not elegantly, but well enough. A ship might arrive at another star system after 1,000 years of travel. A small, tired, genetically altered group of humans might step onto the surface of an alien world. They might not remember Earth as anything more than a myth. They might not even call themselves human in the way we understand the word. But they would be our descendants, our legacy, the proof that we finally broke through the wall. Similarly, I believe we will launch the Newman probes. The first few will fail, lost to the void, or to their own errors. But then, a single probe, launched from an asteroid belt in a distant system, might succeed in building a perfect copy. That copy will build 2 more. Those 2 will build 4. The network will spread. Maybe we will never hear from them because their communication methods will degrade, or because the time it takes for a signal to reach us is longer than we can wait. But they will be out there, silent, replicating, spreading our technological presence across the galaxy like a slow wave. And one day, perhaps 100 million years from now, every star in the Milky Way will be surrounded by the faint signatures of our machines. Not because we intended it, but because we were stubborn enough to keep trying. But that future is not guaranteed, it is contingent on our survival. And survival is the one thing we have not yet mastered. We are a species that has developed the technology to destroy ourselves 100 times over. Nuclear weapons alone could end our entire story within a single afternoon. Climate change is a slower threat, but no less deadly. We have political systems that encourage short-term thinking and discourage long-term investment. We have populations that are distracted, divided, and increasingly distrustful of science and expertise. The effort required to build a generation ship or a self-replicating probe would demand global cooperation on a scale that has never been achieved. It would require resources that could otherwise be used to feed the hungry, cure the sick, or preserve the millions of species that share this planet with us. It would require a commitment that spans decades, not of an individual life, but of entire political administrations and economic cycles. It is not clear that we are capable of that commitment, and that uncertainty casts a shadow. We might not make it. We might be the civilization that burns itself out before it ever leaves the cradle. The generation ships might sit unfinished in their orbital dry docks, scavenged for parts during some future collapse. The von Neumann probes might never be launched because the last of our manufacturing capacity is consumed by war. The stars might remain forever out of reach, not because physics forbids it, but because we could not get our own house in order, so we return to the wall. It is not just a wall of distance and time. It is a wall of our own making. It is built from our biology, our psychology, our sociology, our politics. It is built from the fundamental laws of physics and the stubborn reality of entropy. It is a wall that surrounds us on all sides, and the only way through it is to accept it. Not to give up, not to surrender, but to accept the limits of our situation and work within them with wisdom and patience. We do not need to colonize the galaxy in the next 1,000 years. We need to learn how to live sustainably on Earth for the next 1,000 years. We need to develop technologies that are not just clever, but resilient. We need to build societies that are not just powerful, but wise. And if we can do that, if we can overcome our own worst instincts and survive long enough, then the stars will still be there. They will not go anywhere. And they will wait a little longer for us to grow up. The generation ship and the von Neumann probe are not solutions to our current crisis. They are visions of a future that can only be reached if we first solve the crisis of the present. And that crisis is not about interstellar travel. It is about learning to live together on a single, finite, precious world. We cannot escape ourselves. We cannot run from our biology, or our history, or our limitations. We can only confront them, understand them, and find a way to thrive within them. That is the real challenge. That is the real frontier. And it is a frontier that does not require us to travel a single light year. It requires us to look inward at the wall inside our own minds and find the courage to tear it down from within. Imagine for a moment that you are an alien. Not the little green kind, not the tentacled horror from a horror movie, but something genuinely intelligent, something that can think, calculate, and build. You live on a world orbiting a modest star, in a galaxy of 400 billion similar stars. You have radio telescopes, you have mathematics, you have history, and you have one burning question that keeps you up at night. Where is everybody? This is the Fermi paradox. It has haunted our scientists since the 1950s, when physicist Enrico Fermi, during a casual lunch conversation, looked up at the sky and asked, "But where is everybody?" He meant it literally. The numbers are absurdly generous. Our galaxy is about 13 billion years old. The first rocky planets probably formed within a few billion years of that. That means if even a tiny fraction of those planets spawned intelligent life, and if even a tiny fraction of that life developed spaceflight, then the galaxy should be teeming with civilizations. There should be ancient empires, bustling trade routes, and the cosmic equivalent of highway billboards. There should be alien probes in our asteroid belt, alien signals in our radio static, alien footprints on every moon in the system. Yet, when we look up, all we see is a cold, quiet void. No signals, no megastructures, no evidence of anyone else ever being here at all. It is the most profound silence in the universe. Over the decades, scientists have proposed countless answers. Maybe they all hide from a predatory super race. Maybe they all ascend into digital realms and stop caring about the physical universe. Maybe they all destroy themselves with nuclear weapons or run away climate change or artificial intelligence. Run amok. But there is one hypothesis that ties all these possibilities together into a single, terrifying framework. The Great Filter, The Great Filter is not a thing, it is a concept. Imagine that the journey from a dead world to a starfaring civilization is like a long, dangerous river. There are rapids, there are waterfalls, there are places where the water becomes poison. The Great Filter is a point in that river where almost every boat capsizes. It is a barrier so severe that once you hit it, you either die or you are stuck forever. The filter could be early in the process. Maybe life itself is incredibly rare, and we got lucky. It could be in the middle. Maybe the jump from single cell to complex life is the hard part, and we are one of the only survivors. Or it could be near the end, right where we are now, right at the precipice of interstellar travel. And that is the scenario I find most compelling, because it gels painfully well with the physical and biological barriers we have already discussed. Think about it. Every civilization is born on a world with gravity, with an atmosphere, with a biosphere full of hostile microbes. To get off that world, they must master rocketry, which requires stupendous energy. To survive in space, they must defeat radiation and vacuum. To travel between stars, they must cross distances that would take tens of thousands of years with any engine we can realistically imagine. And they must do all of this while keeping their society stable, while avoiding resource wars, while not burning through their planet's reserves of fossil fuels and rare earth metals. The biological barriers are not just about our own bodies. They are about the evolutionary instincts that drive us. We evolved to compete on the savannah, not to cooperate across light years. We evolved to value immediate food and shelter, not a payoff that takes 10,000 years. So here is the dramatic tension. Perhaps every intelligent species in the galaxy hits this exact wall. They invent radio, they develop a global internet, they build cities that float on clouds, and then they look at the numbers. They calculate the energy needed to send a single generation ship to the nearest star. They realize it would cost their entire planet's annual energy budget for 1,000 years. They realize the ship would take 100 generations to arrive, and by the time it got there, nobody on the ship would remember why they left. They look at their own history of short-sightedness, of wars fought over oil, of environmental collapse ignored for quarterly profits, and they understand the truth. The rational choice is to stay home. This brings us to the economic and social motivation, or rather, the stunning lack of it. We like to think of ourselves as explorers, but humans are, above all, optimizers. Natural selection did not sculpt our brains to dream about distant suns, it sculpted our brains to find the nearest ripe fruit. Our reward systems are wired for short-term returns. You eat a berry, you feel good. You hunt a mammoth, you feast. You build a factory, you make money this year. You invest in a pension fund, you get returns in 30 years. That is about the maximum horizon a human brain can genuinely care about. A project that takes 10,000 years, with no guarantee of success, no way to see the results, no way to tell your grandchildren that you were right. That is not just difficult, and it is anti-evolutionary. Economists and game theorists have studied this. They call it the intergenerational dilemma. A society must decide whether to spend massive resources now for a benefit that will only be realized by people who do not yet exist. The rational choice, according to game theory, is to defect. Spend those resources on things that help people alive today. Build hospitals, feed the hungry, fight the next war. Do not build a starship that will launch after you are dead. The argument becomes even stronger when you consider discount rates, the economic principle that future benefits are worth less than present benefits. If you have a discount rate of, say, 5% per year, then a benefit that arrives in 10,000 years is worth essentially zero today. From a purely economic standpoint, interstellar colonization. Now, I know what you are thinking. What about curiosity? What about religion? What about the pure, stupid, human drive to go somewhere just because it is there? Sure, those impulses exist. They are real, but they are rare. They are the exception, not the rule. Throughout history, exploration has almost always been tied to economic gain. The age of exploration was about spices and gold. The space race was about national prestige and military advantage. There has never been a major space program whose primary motivation was abstract wonder. And even if a society did have a culture that valued interstellar exploration above all else, they would still need to overcome the physical barriers. They would still need to build a ship that can survive for millennia. They would still need to keep a crew sane and stable for 1,000 generations. And most importantly, they would need to keep that project funded and politically supported for 1,000 generations. One war, one economic depression, one religious revolution, and the whole project gets scrapped. The ship, if it even exists, rots on the launch pad. And this is where the great filter becomes not just a hypothesis, but a stark prediction. If we look at our own civilization, we can see the pressure building. We are 100 years into the space age, and we have not left low Earth orbit in a meaningful way since 1972. Our space programs are retreating, not advancing. We are more likely to argue about satellite constellations than to plan for a Mars colony. And even those plans, the ones for Mars, they assume we can terraform a planet with a nearly non-existent atmosphere and a deadly radiation environment. They assume we can somehow breathe. They assume we can somehow grow food. They assume we can somehow keep our bones from dissolving in microgravity. Every decade that passes, the barrier looks a little higher. Every new report on the health effects of space radiation, every new study on the toxicity of Martian soil, every new analysis of the absurd cost of lifting mass out of a gravity well, makes interstellar travel look less like a dream and more like a fantasy. So let me lay out the implications, because they are genuinely sobering. If the Great Filter exists, there are two possibilities. Either the filter is behind us, meaning we have already survived the hardest part, or it is ahead of us, meaning the hardest part is still to come. Which one is more likely? Look at the history of life on Earth. It took 1 billion years for the first cells to appear. It took another 2 billion years for multicellular life. It took another 600 million brains. And then it took only a few thousand years for us to build nuclear weapons. We are a species that is very, very good at creating existential risk. We are very good at inventing technologies that can destroy us faster than we can develop the wisdom to use them responsibly. Climate change, nuclear war, engineered pandemics, runaway artificial intelligence, any one of these could extinguish our civilization within the next century. And none of them require interstellar travel to solve. This suggests that the Great Filter is not behind us. It is ahead of us. We are not the survivors. We are the ones about to hit the rapids. Every other civilization in the galaxy probably reached this exact point, looked at the numbers, and then either destroyed themselves in internal conflict or simply gave up, content to manage their own planet, to watch their own suns burn out, to live and die within a single solar system. They became what we might call a solar system-bound species. They never escaped. They never colonized the galaxy. They never built a Dyson sphere or sent a laser-powered probe to the nearest star. They just sat there, in their own little cradle, and eventually they faded away. And that is the answer to Fermi's question. Where is everybody? They are trapped. They are at the bottom of a gravity well, surrounded by a vacuum that kills them in seconds, bathed in radiation that slowly destroys their DNA, weighed down by chemical rockets that can barely achieve escape velocity. They are us if we are not careful. The sky is silent, not because life is rare, but because life is forever trapped. The stars may be empty, not because we are alone in a special chosen way, but because intelligence is a dead end. It is a local maximum, a plateau from which there is no escape. Evolution builds brains that are good at solving immediate problems, good at competing for territory, good at inventing tools. But it does not build brains that are good at building starships. And so, everywhere in the galaxy, intelligence emerges, it invents radio, it looks up, it dreams, and then it hits the wall. It realizes the cost. It gives up. It burns itself out in petty squabbles over resources it cannot bear to leave behind. Maybe, there is a civilization out there that made it. Maybe there is a species that evolved in a different way, with a different reward structure, with a culture that valued long-term investment over short-term gratification. Maybe there is a species that built their starships not out of economic necessity, but out of pure, irrational faith. If such a species exists, they are not talking to us. They are not here. They are out there, somewhere, doing the impossible. And we will never know them. Because we, like almost every other intelligence in the universe, are likely to stay right where we are. We will argue about politics. We will burn fossil fuels. We will bicker over borders. We will watch as our planet slowly becomes less habitable, and tomorrow will never come. The wall we have been exploring is not made of rock or metal. It is made of our own minds. It is made of biology, economics, and physics. It is made of the cold, hard mathematics of rocket equations, and the even colder, harder mathematics of human nature. And if we cannot tear down that wall from within, if we cannot learn to think in terms of millennia instead of elections and cycles, then we will join the silence. We will become just another data point in the great filter, just another civilization that almost made it, just another species that looked up at the stars and said, maybe tomorrow, but tomorrow, in the vast, indifferent clockwork of the cosmos, never arrived. And this is where the wall becomes truly formidable, because it is not just a wall of physics, it is a wall of time itself. Is 4.24 light years away. That means even if we could travel at 1% of the speed of light, a speed that is currently a fantasy, but maybe not a physical impossibility, it would take over 400 years to get there. 400 years. The Pilgrims landed at Plymouth Rock 400 years ago. The English language was barely recognizable to modern speakers. The scientific revolution had not yet begun. A ship. Imagine launching a ship today, a ship that carries 100 people, a ship that must be completely self-sufficient for 4 centuries, and telling yourself that you have any control over what happens on that ship after you are dead. You cannot. The ship is a world unto itself. It will develop its own politics, its own culture, its own religion. It will experience plagues, rebellions, and moments of profound doubt. The people who arrive at Proxima Centauri will not be your people. They will not speak your language. They will not remember your name. They will be a new species, shaped by the unique conditions of their vessel. And the question becomes, why would you bother? Why would any society pour its entire treasury into a project that produces not a single identifiable benefit for 1,000 years. A project that creates a civilization that is, for all practical purposes, a stranger. The economic argument against interstellar colonization is so overwhelming that we must consider the possibility that it is not just an obstacle, it is a proof. It is a mathematical demonstration that purposeful, crude colonization of other star systems is not just difficult, but fundamentally irrational. The only way it could happen is if there is a force stronger than economic rationality. And what forces are stronger? Fear. Desperation. An existential threat so overwhelming that staying home becomes worse than leaving. A dying star, a rogue planet on a collision course, a biosphere that is becoming uninhabitable. In those cases, a civilization launch, generations be forced to launch generation ships simply because there is no other option left alive. But then, we must consider the nature of such a forced migration. It would not be a glorious, well-funded project of an enlightened civilization. It would be a desperate scramble. Ships would be built hastily, with inadequate life support, with flawed genetics, with populations that are traumatized and fearful. The success rate of such desperate launches would likely be near zero. The ships would fail, or the crews would tear themselves apart, or they would arrive at their destination only to find that their new world is just as hostile as the one they left. Desperation does not breed success, it breeds collapse, and this brings us to a deeper, more unsettling biological barrier. But we are adapted to a very narrow sliver of conditions. We need a specific range of temperatures. We need a specific gravity. We need a specific atmospheric pressure. We need a specific mix of gases. We need a specific day-night cycle. We need a specific magnetic field to deflect cosmic rays. We need a specific ozone layer to block ultraviolet light. We need a specific microbiome of bacteria. We are specialists for a single planet. And the universe is filled with objects that are not Earth. Every other world is a death trap. The most habitable world in the solar system, Mars, has a surface pressure that is less than 1% of Earth's. It has no magnetic field. It has no ozone layer. Its soil is laced with perchlorates, chemicals that attack the thyroid gland. Its gravity is 38% of Earth's, and we have no idea what the long-term effects of that are on human development. A child born on Mars would grow up unable to ever visit Earth, because their bones would be too weak to withstand Earth's gravity. They would be a different species, perhaps within a few generations, and we are talking about the nearest planet. The distances between stars dwarf anything in our solar system. The conditions on planets around other stars are completely unknown. We might arrive at a world that is perfect in every way, except that its day is 40 hours long, which completely disrupts our circadian rhythms, or its atmosphere contains a trace element that is harmless to the native life, but slowly dissolves our neural tissues. The variables are infinite, and the tolerances are, for land-dwelling animals like us, incredibly tight. There is also the biological barrier of the microverse. We are not just individuals. We are ecosystems. Each human body contains trillions of bacteria, viruses, and fungi. Our immune systems are tuned to the microbial life of Earth. If we land on a world that has its own independent biosphere, its own set of bacteria, its own viruses, its own prions, our immune systems will have no defense. The alien microbes may not even need to be pathogenic in the traditional sense. They could simply be too efficient at consuming the resources our own microbes need. They could outcompete our gut flora, leading to starvation from the inside. They could attach to our nutrient surfaces and block nutrient absorption. They could trigger anaphylactic shock, by presenting proteins that our immune systems interpret as lethal threats. So, the history of Earth is filled with the decimation of isolated populations by new diseases. The indigenous peoples of the Americas were devastated by smallpox and measles, diseases that Europeans had lived with for centuries. That was a single planet with a shared evolutionary history. An alien biosphere would be completely foreign. Even if it is harmless by its own standards, it might be lethal to us simply because our bodies have never encountered anything like it. We would be like a rainforest frog dropped into a desert. We would not adapt. We would die. This means that any successful interstellar colonization must involve complete sterilization of the target world. It must involve terraforming on a scale that exceeds anything we have imagined. We would have to strip the alien biosphere entirely, or we would have to live in sealed domes forever. And what is the point of travelling for 400 years across an abyss of vacuum to live in a dome? Why not just build the dome on Earth? The question answers itself. The dream of colonization falls apart. When you look at the biological realities, the universe is not waiting to welcome us. It is waiting to kill us. In 1,000 ways we have not even discovered yet, and so the great filter tightens its grip. And we have a biological and economic trap that may be inescapable. The silence we observe is not a mystery to be solved by finding the aliens. It is a message to be read by understanding ourselves. Every other civilization that reached our level of technology probably looked at the same equations, looked at the same biological hazards, and made the same calculation. They decided that the cost was too high. They decided that the dream of the stars was a beautiful lie. They turned inward. They managed their own planet. They built art and culture and philosophy. They found meaning within their own solar system. And then, eventually, their sun died. Or their planet, they exhausted their resources. They slipped into the long, dark night of a species that never left home. They became fossils on a dead world, waiting for a future intelligence to dig them up and wonder who they were. And that future intelligence will never come, because the same wall awaits them. The great filter is not an event, it is a constant. It is the inevitable endpoint of intelligent life in a universe that does not care about our ambitions. We are not special. We are not the first. We are not the last. We are just another in a long line of hopeful species that looked up, saw the stars, and then stayed home. The only question that remains for us is how long we will sit in our cradle before we burn it down. And yet, here we are, after all that doom and gloom, after the cold equations and the cosmic's silence, after realizing the stars are not waiting with open arms. What do we do? Do we just give up? Do we pack it in, stare at the ceiling, and wait for the asteroid or the climate collapse? No, absolutely not. Because here is the thing about this cradle. It is not a cage. It is a launching pad. We just have to stop obsessing over the one thing we cannot reach and start building the one thing we can. Let me tell you a different kind of story. A story of what is actually possible. If we take our heads out of the interstellar clouds and focus on the real estate we already own. Mars, the red planet, it is not a vacation spot. It is a toxic, freezing, radiation-blasted desert with an atmosphere so thin it might as well not exist. But you know what? It is also a whole world. A world with water ice, with carbon dioxide, with minerals, with gravity. Roughly a third of Earth's. A world you can actually stand on. And we have the technology right now, today, to start building a self-sustaining colony there. It would be hard. It would be dangerous. People would die. It is not magic. It is engineering. And beyond Mars, we have the asteroid belt, $1 trillion resource field floating in the black. We are talking about platinum, group metals, rare earth elements, water, carbon, all the building blocks of an industrial civilization just drifting around waiting for someone to show up with a shovel and a smelter. We do not need to go to Alpha Centauri for resources. We have a whole belt of them right in our own neighbourhood. We can build massive space habitats out of this stuff. O'Neill cylinders spinning at exactly the right speed to create artificial gravity. Huge windows letting in that warm, familiar sunlight. We can build cities in the void. Then there are the moons of Jupiter and Saturn. Europa, with its global ocean hidden beneath miles of ice, potentially teeming with life. Enceladus, shooting geysers of water into space like a cosmic fire hose. Titan, with its thick atmosphere and liquid methane lakes. A world so strange it feels like science fiction. But it is real. We can build research stations there. Underwater habitats. Mining outposts. Ghosts. Colonies under domes. Not comfortably. Not easily. But we can live there. And do not even get me started on the Oort cloud, that distant, frozen shell of comets surrounding our solar system, stretching out a full light year from the sun. That is not empty space. That is 1 trillion frozen rocks, each one full of water and organic compounds. If we ever figure out how to live in the deep dark, the Oort cloud is a whole other frontier, a resource base, so vast it boggles the mind. We could build habitats inside. We could set up refueling stations for robotic missions. The solar system is not small, it is huge. It is 120 billion kilometres across. That is a lot of room. So when I say interstellar travel is likely impossible for biological humans, I am not saying we are trapped in a tiny prison. I am saying we have been given a palace the size of a star system, and we are sulking because we cannot have the mansion next door. That is ridiculous. That is ridiculous. It is our whole universe for the foreseeable future, and it is enough. Think about it. A Dyson swarm around the sun. That wild idea from the 1960s, a sphere of solar collectors harvesting the entire energy output of our star. We could do that. We have the materials in the asteroid belt. We have the energy from the sun. We have the robotic technology to build autonomously. It would take centuries, maybe millennia. But it is not a pipe dream. It is a logical endpoint for a technological civilization that refuses to die. We could have energy to spare for 1 billion years. When we could terraform Mars. Sure, but why stop there? We could make the entire inner solar system habitable. This is not escapist fantasy. This is realistic optimism. This is looking at the constraints of physics and saying, okay, you win on interstellar travel, but we are going to make this system a paradise anyway. We are going to build a civilization that stretches from the orbit of Mercury to the edge of the Kuiper belt. We are going to have millions, maybe billions of people living in space, on worlds, in habitats. We are going to have art, and music, and science, and love, and all the messy, beautiful things that make us human. And we will not be running away. We will be building a home. And here is the twist. The very same barriers that keep us from the stars are the best motivation we have ever had to protect the Earth. Because think about it. If we could just hop in a starship and leave, where is the incentive to fix the mess we have made? Why would anyone bother with climate change if they could just buy a ticket to a new Earth light years away? Why would we care about nuclear weapons if we could just evacuate the planet? Interstellar travel, if it were easy, would be a get-out-of-jail-free card. We would be the worst kind of tenants, trashing the apartment, and then skipping out on the rent. But we cannot skip out. There is no escape. So we have to stay. We have to learn to live here. We have to fix our own home. It is like a marriage. You cannot just walk out the door every time things get hard. You have to sit down and figure it out. And humanity, for all our flaws, is capable of the most incredible cooperation when the stakes are high. We have eliminated diseases. We have reversed environmental damage. We have pulled ourselves back from the brink of war more times than I can count. We have to do this because there is nowhere else to go. Mitigating existential risks on Earth is not just a nice idea. It is the single most important project of the next 100 years. Climate change is real, but we have the technology to fix it. Nuclear war is a nightmare. Nuclear war is a nightmare, but we have diplomacy to prevent. Pandemics are terrifying, but we have the science to fight them. We just need the will. We need to look at the silent, empty stars and realize that they have just given us the greatest gift. They have forced us to grow up. They have forced us to take responsibility. We cannot run away, so we must learn to stay. And staying does not mean stagnation. It means building a civilization so resilient, so self-sufficient, so magnificent that no single disaster, no asteroid, no supervolcano, no solar flare can wipe us out. We spread across the solar system. We diversify. We become a multi-planetary species, not running from Earth, but protecting it, supporting it, celebrating it. The challenge of space is not escaping Earth. The challenge of space is making Earth a place worth staying and then building a civilization that spans the solar system anyway. That is a goal achievable within our lifetimes and within our physics. We do not need warp drives. We do not need wormholes. We do not need to break the speed of light. We need existing technology, political will, and a sense of purpose. We need to look up at the night sky and see not a prison, but a playground. An endless, beautiful, dangerous, and profoundly abundant playground. So here is the call to action. And I do not mean the kind where you click a button and feel better about yourself. I mean a real one. If this video made you think differently about humanity's place in the cosmos, share it with someone who dreams of starships. Share it with that friend who watches Star Trek and feels a pang of sadness that we will never have that future. Let them know the real frontier is right here. It is in the deserts of Mars. It is in the ice of Europa. It is in the rocks of the asteroid belt. It is in the solar collectors we have not built yet. It is in the Oort cloud we have not even reached. It is in the decision we make right now, today, to stop mourning the stars we cannot touch and start building the future we can. Because the universe is not punishing us. It is giving us a choice. We can be the species that looked at its limits and gave up. Or we can be the species that looked at its limits and said challenge accepted. I know which one I am betting on, and I think you do too, so go outside tonight. Look at the moon. Look at Jupiter. Look at that faint, dusty band of the Milky Way. And know that you are looking at your home, the whole thing, the entire solar system. It is ours. It is waiting. And the only thing stopping us is us. So here we are, at the edge of everything, looking out into a darkness that goes on forever. We have walked through each barrier together, piece by piece, and the picture that emerges is not one of cowardice or failure, but of a universe that simply does not care about our ambitions. We have the fuel problem. The tyranny of the rocket equation, which demands that for every pound of payload you want to send to the stars, you need 1,000 pounds of fuel just to get it moving. We have the radiation problem, the endless sleet of cosmic rays that will shred our cells, damage our DNA, and slowly cook anyone foolish enough to spend years in deep space. We have the biology problem, the fact that our bodies are calibrated for a very specific gravity, a very specific atmosphere, a very specific magnetic field, and that taking them away from that home for too long means muscle atrophy, bone loss, blindness, and 100 other slow, quiet failures. We have the psychology problem, the crushing isolation of being millions of miles from the nearest human voice, trapped in a metal can with the same faces for years, knowing that rescue is a fantasy and that you will likely die before you ever see green grass again. And we have the economics problem, the simple, brutal truth that no government or corporation on Earth has the money, the political will, or the stamina to dedicate lifetimes of funding to a project that will not pay back for generations. Every barrier we have talked about is real. Every one of them is hard. And together, they form a wall so tall and so wide that it can feel like the universe is actively trying to keep us in our cradle. But that is not quite the right way to think about it either. The universe is not trying to do anything. It is just what it is. And what it is a place of extremes. A place where the distances are so vast that our minds cannot truly grasp them. Where the temperatures and pressures and energies are so far beyond what our biology can handle that sending a human being into interstellar space is not just an engineering challenge, it is almost an act of defiance against nature itself. We are water and carbon and fragile membranes. We are built for a warm, wet, thin atmosphere world with a big moon to hold us steady. And yet, we are not built for the void. And yet, because we are also the species that looked at the ocean and said, I will cross it. We are the species that looked at the sky and said, I will touch it. We are the species that strapped ourselves to a controlled explosion and rode it to another world. So maybe the real question is not whether we will escape the solar system, but whether we can become something different enough to do it, whether we can merge with our machines, or engineer our own biology, or learn to sleep for centuries in suspended animation, whether we can solve not just the physics, but the politics, not just the medicine, but the madness, because the barriers we have talked about tonight are formidable, but they are not magical, they are just problems. And problems have solutions. The only question is whether we have the time, the money, and the collective will to find them before we destroy ourselves or lose interest. But for now, for this moment, let us sit with the reality of where we are. We are on a beautiful blue marble, dwarf star, spinning around a yellow dwarf star in a quiet corner of an ordinary galaxy. And we are the only conscious minds we know of who have ever looked up and wondered. That is a gift. That is a responsibility. And it is also a kind of prison. Because the universe did not make us to leave. It made us to live. And perhaps that is the greatest filter of all. The filter that says, you are here. You are here. You are home. You are not going anywhere. Or change everything about who you are. What do you think? Are we really stuck? Or will future breakthroughs change everything? Maybe someone out there is already sketching designs for a warp drive in a notebook. Maybe the next generation will laugh at how pessimistic we were. Or maybe they will look back at us and say, they were right. Let us know in the comments. We want to hear your take. Every crackpot idea, every ray of hope, every cynical rebuttal. The conversation is what keeps this alive. If you enjoyed this journey through the cold, hard truths of interstellar travel, please take a moment to like this video and subscribe to the channel. It helps more than you know. And if you are hungry for more, you should definitely check out our video on the Fermi paradox, where we ask an even more unsettling question. If the universe is so big and so old, where is everybody? Or watch our guide on how to survive on Mars, because hey, baby steps. Let us at least get to the next planet before we worry about the next star. We want to extend a huge thank you to the artists and musicians whose work brought this video to life. Their visuals and sounds are what made the empty darkness feel real and terrifying and beautiful all at once. Full credits are in the description below. Thank you for watching. Thank you for thinking. Thank you for being one of the few who still looks up. The stars are waiting, and whether we ever touch them or not, the act of trying is what makes us human. So keep dreaming, keep asking, and maybe, just maybe, keep building. Good night.